Giuseppe Maggiore, and let me welcome you to Lecture 5 of the Introduction to C# course. Today we're going to focus on a new topic, functions and the stack memory. So, obviously we've seen code in just a single huge file where everything just happens into the same program, and at some point we will feel the need to organize this code as it grows into smaller logical units. And these logical units are functions. Organization here has actually, you could say, two implications. One is we have to identify which blocks of this big mountain of code are somehow independent, because in order to split things, you have to identify things that can be split, and if they can be split, it means that they are not interconnected with everything. They are somewhat already separate, at least conceptually. And then we have to give them a name, because, well, just splitting is not enough. If you split something and you put it aside, how can you recall it later when you need it? And so this is kind of the core of functions. Functions are essentially meant for splitting code in this big file and to giving the code we split a name. So functions will encapsulate an independent piece of code, give it a name, but also, well, because it's an independent piece of code, it will accept some inputs that will influence the behavior of the function, return an output to signal whatever the result of the computation of the function was, and they even have an isolated scope, remember, of variables, just like the block of an if then else of the code block of a loop, so that only the active instance of the function may access its own special little variables. The general syntax of functions in C# is quite close to that of the C, C++, Java languages, and in general is quite, the common syntax. We have the return type, so we start with whatever the function returns. Then we have the name of the function. Then we have a series of parameters, which are basically variables that will be injected into the function, and then we have the body of the function. So the return type can be any type, like int, double, custom types, etc. The function returns something which I will often refer to as the output of the function, because in my head the most important outputs we deal with are the outputs of the modularized units within our code. So yeah, a function has an output, gives something back, and also has an input, which are the parameters, which are a series of variables that we bind with a value when the function is activated, so when we want to compute with this function. And then the body of the function, of course, is just a series of statements containing return, which is a special kind of statement to which we give an expression of the same type of the return type, and whatever value this expression takes will be the output of the function, and then the body is stopped. So return is always the last statement executed in a body. Okay, now let's start with a useless example. Void. The type that this function will return is void. Say hello, no parameters, and then console.writeLine. Hello. Okay. So, return type, name, parameters, body. In a function like this, we would be allowed to say return and then directly the semicolon, because there is no proper expression with a value of type void. Whenever we have return, we stop the execution of a function. So if you have a condition then based on something dynamic, and inside the condition you return, and then you have more code afterwards. This code on line 14, whatever it may be, will be skipped if the condition on line 12 happens to be true. So it's still possible to return, but this is an outputless function. Some people call these procedures, but that's a little bit of an old name. It's a historic name, you could almost say. Okay. We can activate this function or invoke it as follows. Let me start the compiler. .NET Watch build. .NET run. And we get to see hello. Okay. What's the point of this? Well, let's say that we have different programs, different parts of our program. Like we want to call this say hello function. We want to print hello into many places. So we have, I'm going to simulate, this is not just one line of code with 3 dots, but it's actually more code, So there's code everywhere, and we want to be able to say hello in many places because this is an important part of our program that happens all over the place. By having this into a function, we can actually change the behavior of various parts of our program by only changing the body of the function. So let's say that all of a sudden, in all the places where I say hello, I want to say hello with 3 exclamation marks. There you go. I change it once, and the change is automatically propagated in all the places in the code that are basically pointing to the body. So you could imagine that basically what the compiler is sort of doing, even though this is quite inaccurate, is copying the body of the function into every place we put the name of the function. That's very handy. So this is basically a link between code. So line 14 is linking to line 10. Line 16 is also linking to line 10. Line 18 is also linking to line 10. And because you have all these lines converging to line 10 from all over the places, all over the place in our program, then yeah, if we change whatever is pointed at by line 10, then all the things that point to line 10 will also change accordingly. So this is very handy. It's a way to propagate changes more quickly. Also, another little note, we could move this say hello function to another file at some point. So by grouping together little definitions like this say hello function into separate independent files, what happens? What happens is that slowly but surely our program will eventually be split into different compilation units, the files, and then maybe the files will be grouped into projects, etc. And this is the fundamental tool to manage organization of code in applications. In this course, it's an introductory course, there's no reason whatsoever to split things into files, but in real life, this will be the first step towards the first split, which is splitting code into functions, and then the functions will go into separate files, and eventually into separate classes, and then into separate projects and DLLs, and so on. Alright, now we could extend our function with some intelligence. Well, okay, intelligence between between quotes. So for example, let's say that, yes, how many exclamation marks will be a parameter. And so instead of just hello and then just an exclamation mark, I will start with exclamation marks being empty, and then for I0 to how many exclamation marks. I really don't need these curly brackets. Exclamation marks is exclamation marks plus 1 exclamation mark, and here we can put the exclamation marks at inside the string itself. Okay. Notice, and this is really important, we've introduced 6 compilation errors. Changing the structure of functions, adding parameters or changing a return type is very useful because sometimes it can be a way to basically use the compiler as a to-do list. The best refactorings in code rely heavily on changes in types in such a way that the compiler must tell you and helps you to find out all the places where you have to apply a change. But sometimes you can also decide to be retrocompatible. So now there's this parameter, how many exclamation marks, and it needs to be provided. So in the first case, I will have 3 exclamation marks, 2, 2, 1, 5, and 4. Okay, now the compiler is happy. And, well, the thing also works, which is nice. Let's take a look at what's happening here. Here I put a value. This is an argument. The values or the expressions, because there could be variables that we put in here, 3 is bound or assigned to how many exclamation marks. And then 2 is bound to another instance of how many exclamation marks in a new scope. And also here. And also here. Just one minor note I want to share before we dive into the way this thing works. We can also provide a default value. And this is the retrocompatibility I mentioned. We could say that, well, whenever we don't provide a value, the value is 1. I have also done this in practice, like adding a parameter without a default value, using the compiler as a to-do list, changing only the bits that I recognize, okay, these really need to be changed, and then, and only then, providing a default value for the instances that I don't need to change. Okay, anyway. Let's put a breakpoint here. And let's see what happens if we run this with the debugger. This is going to be very interesting because we're going to find out something about this block of the debugger here called the call stack. Okay, you see here, there are no variables. Let me fix this. Let me say that there is a lone variable which, I don't know, says yar. Doesn't matter that much, but I want to have a lone variable here. I also want to print it. Just, I don't know, to have to do something. I don't like warnings that complain about a variable not being used. Okay. No, I'd rather not enable dictation. Okay. Okay, look at this. Here, the variables contain, okay, the args and our lone variable. Okay. Say hello of 3. I'm not going to press this button, step over or F10, because this will actually go to line 21. I want to press step into. This is interesting because code has this fractal nature. It can be nested until arbitrary depths. Then at every moment in code, we could dive into the code and sort of increase the level of resolution of our reasoning, if you will, or we can say no, I'm good here at this level of resolution and abstraction, so just move to the next step. It's very interesting. So there is not just one way to go forward. You can go forward with a big step, so line 19 to 21, or a small step and see what happens to the say hello function, which might be insanely big and complicated, by the way, but we'll step into. Now, I want you to look at what's going to happen at the call stack block. Are you ready? 3, 2, 1, step into. Ooh, bam, the call stack has changed. And this is really important in order to be able to understand what is happening to our functions and how functions work. I've actually had to debug some beautifully nasty, rich bugs that had to do with the way memory is managed. One quite recently, actually. Okay, now, how many exclamation marks is here? So now we have, look, 2 variables. How many exclamation marks and exclamation marks? And we miss one, my lone variable. Very interesting. How is this possible? Well, how this is possible is because the call stack has introduced a new area of memory, which is the scope of this specific call to the say hello function in memory, and there all the variables for this specific run of say hello, because say hello will run 6 times in total, but for this one we are going to use this block in the call stack. And you can see here that it says, okay, this is say hello, line 11, blah blah blah, but we can also see that, well, line 19 still there, it's frozen. And if we click on line 19, okay, now things get interesting, because you see the color also of the marker of line 19, it's this sort of greenish, because it's active and yet sort of frozen at the same time. Whereas here on line 11 we have, a proper yellow. And you can also see that plenty of things are switching in the colors and the highlight to really show what is happening. It's very beautifully done, this debugger. So if I say, okay, I want to see the call stack, so the scope at the caller, the program, the main, and then I get to see it. And for the main, we are at line 19. And there's one variable, my lone variable, here among the locals and the args. Okay. But we can also say, no, I now want to zoom into what's happening inside say hello. And now in the locals, we actually have other variables. And my lone variable, how many exclamation marks, and the exclamation marks variable, they all exist, just in different partitions of the stack. Now I can step over. You can see now we also have variable I. This is executed. Well, there's nothing special about this. Then let's put another breakpoint here. Okay, now variable I is cleaned up, obviously, because that's another subscope inside this block of stack memory. The next step, what's going to happen? Well, the scope of say hello is not needed anymore. We printed hello, this function run has finished, has terminated. So look at what happens now with the stack memory as I step over. Are you ready? There are 2 blocks of stack memory, because right now we're active at 2 instructions. Instruction 19 in the main scope, instruction 14 in the say hello scope. And ready? 3, 2, 1, tack. The stack is popped. So the top element of the stack, which is the current function, is cleaned up. And because functions always unfold from the top back to the bottom, so the current function is the only one that's really active, so it's the only one that might actually end up popping. That's why we call this a stack. You call a new function, you push another block on top of the stack with all the variables and data for that function. That the top function is done. Those variables are all cleaned up in one fell swoop by popping the top of the stack. So the stack is also a very efficient data structure. We go to the next step. Now there's only one item on the call step, on the call stack, which is the main program. I step into. Oh, no, that's not allowed, because on Mac step into is also something else, I guess. Okay, let's press the button, step into. Oh, now the value of 2 is put into how many exclamation marks. So actually, plenty of things are happening. That's why it's important to at least know at a basic level how many things are actually happening. Then you can just ignore them. For most scenarios, it's going to be fine to ignore these details. But yeah, they are happening anyway, and not knowing how this delicate machine works can and will screw you up if you don't have it under control. Anyway, first, the call stack is extended. We push another block on top of the call stack. Then, inside this top block of the call stack, we allocate, we make room for the two variables, how many exclamation marks and also I, because I also has to be factored in. So literally these variables are counted in order to know how big the call stack location has to be. It's going to be 4 bytes plus, I think this is also 4 bytes because it's a pointer. Unless this is a 64-bit processor, then it's going to be 8 bytes. But anyway, so it's a bunch of bytes, counting how many variables actually need to have room made for in the call stack. Okay, so the call stack is allocated, and the variables claim space in the call stack, and then the values are put on the parameters. So all the arguments, in our case, just the value 2, is assigned to this parameter. How many exclamation marks? And you see it's 2. Then we can run the actual function. When we come to the end of the function by means of either a return statement or just reaching the last statement of the function, then the call stack that's on top of the stack gets cleaned up, and then step over or step into actually produce exactly the same result, and we move back to the main program. So you can see line 21 is shifted from greenish to yellow, yellow meaning this is the actually active line of code, and there are no other lines of code active at the moment. Something useful to know is that this button here, continue, runs until the next breakpoint is hit. So we're going to hit it every time the say hello function is invoked and comes to its rightful termination. So this can be very useful, to also introducing functions is also an interesting way to have places for our debugger breakpoints to be hit. Now, functions may return results, and these results can be used by the caller of the function by treating the function invocation like we would any other expression. Okay, that's quite a mouthful. So let's say that I have a function, largest, which takes 3 values, x, y, and z. And this function will return which of these 3 values is the largest. So it will return one of the 3 values. So when x is greater than y, then, okay, so x is greater than y, so it's either x or z. But if x is also greater than z, then, well, we return z. This is going to be quite a long expression. Otherwise, if y is greater than x and y is greater than z, well, then in this case it's y. And otherwise, well, otherwise it's probably z, right? Okay, very good. So, let's make this a little bit more interesting. Let's say we have 3 variables, a, which we parse from the console.readline. And wait, yeah, well, I'm very happy we finally have these compiler warnings where finally C# is moving yet another step up in the quality of programming languages, and this is very exciting. Okay, so then we have A, B, C, and we have these 3 values. No clue which one is going to be the largest, and I can simply call largest of A, B, and C. First of all, let's test this. Just, I don't know, a matter of, you could say, hygiene, if you will. So let's test this. .NET Run 1, 2, 3, and oh, it would also perhaps be nice to print at least the value. Now this is a testing program, so I'm not even going to put the nice nice little writings that say what's happening, etc. I'm just going to keep it like this. So .NET Run 1, 2, 3, and it prints 3. Okay, makes sense. .NET Run 4, 5, 3, and we get 5. Okay, that's good. .NET Run 10, 9, 8, we get 10. Now, 1, 1. Oh, what have I done? 1, 1, 2. And we get 2. Okay. 2, 2, 3. And we get 3. 3, 3, 2. We get 2. Oh, 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 oh. Ha 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 ha. And we found a mistake. Okay, this is interesting, and it's also an interesting technique that I might have, let's say, accidentally ended up showing you. Now, our code was able to find the greatest element when there is a greatest element, but sometimes you can have multiple values that are the greatest at the same time. And so actually for the largest, we have to extend our program with equality. And I tested 332, which is quite an interesting input because, well, the first two values are the greatest at the same time, but because x and y are not strictly bigger than the other two, because, well, x is not greater than y and y is not greater than x, we fall back on the third value. So what is the trick here to be learned? Whenever you're thinking about how to test something, that's also why writing tests and unit tests, which some people consider to be a sort of magic activity, it's very, very, very difficult. It's almost impossible to get tests to really cover the things you haven't thought about, because that's where the really interesting bugs will be hiding, in the places you haven't yet thought about. But anyway, so learning how to think about the so-called edge cases, so the interesting, slightly more challenging inputs, thinking about the weird scenarios. That is what testing is about. And as developers, we have a tendency, especially when testing, to test with our big blind spot of testing the things we put into our code logic. But what we need to learn to do is to learn to test what we didn't put, the things we didn't consider. So that's why you should always try the weird inputs, empty array, malformed inputs. You should try well, in this case, the weird scenario where not one of the values is bigger, but two of the values are the biggest, you know? So, yeah, this sort of thing. So, the ability to test, like an old colleague of mine used to call this the grandma testing, pressing all the buttons like a madman, uh, never waiting for one input to complete, putting in the worst possible quality of inputs, etc. Anyway, enough with this. So let's look into the output of this function, because largest is a function with an output. This function produces an output of type int, meaning that we will return an expression. Well, the function doesn't do anything but return an expression, which will need to have type int. We could have also changed this, of course. If x is greater equal than y and x is greater equal than z, then we return x. If, and then let's pick this condition, then we return y, and finally we just return z. Notice how I'm using this pattern of just having the return, because if the condition on line 11 is true, then the statement return x will be run, and this will effectively stop the function from running anything else. So if we hit this, then line 12 is never going to be executed. We skip the rest of the body. And if we hit the return statement on line 12, well, then line 13 is just not going to happen. So this is sort of an alternative to else statements. We could also make this more explicit. Well, really up to you what you prefer. There is truly there is truly no better way of doing this. I would argue the if then else makes it a lot more explicit that you are discarding another piece of code, and it can be very difficult to reason about a function with a lot of code when there are return statements scattered around the code, because they make the code less uniform to reason about. Anyway, when a return statement is encountered, then the stack frame on top is cleaned up. This we know already. Variables x, y, and z cease to exist. This expression, on the other hand, is the only thing that survives the stack frame elimination. So this value that is returned will be given back and will be put in the place where we had the function, as if the function had just been an expression calculating and reducing down to that value. And that value in our case will then be assigned to A, B, C. Let me show you this in action. Let's start the debugger up. Okay, the debugger is not doing much actually. I'm slightly puzzled by this. Let's see what's happening. Okay, so the program is here. Did I save? Oh, perhaps I did not save. Oh, okay, whatever. Okay, let's start the debugger. Again. Oh my god, yes, of course. We're stuck at the read lines. Yes, very good. Okay, so 1, 2, and 3. Okay, so the inputting of the input is not really working as I would like it to work. So let's simplify our lives a little bit. 3, 3, and 2. Okay. I don't want to fight the debugger for this. And the way you put input in the debugger console. So I hope you'll forgive me for skipping this for a moment. It's also quite common actually to zoom into a particular input and using that as the basis for your debugger, and then forgetting to uncomment the console.read lines, for example. This would be the classic way of doing this. Okay, anyway, we have A, B, and C. We have variable ABC, which belongs, to the main scope. That's why returning a value is sort of a way to create a warp gateway, if you will, that links the scope inside the function to the scope outside the function. Let's enter largest. X, Y, and Z have been assigned to the values of the expressions passed as arguments. So expression A is evaluated, the result is 3, but this could have also been a very complicated expression like A plus B minus C or whatever. Then it gets evaluated, the value gets put into X. Then we do the same for the second expression here, the second argument, and the value is put into Y, and finally the value of the third gets put into Z. Then we start executing the actual function. So step over is X greater or equal than Y and also greater or equal than Z. What do you know? It is. So we hit the return statement. Okay, now plenty of stuff is going to happen now because this is a return statement. So yes, the stack frame will be cleaned up. Okay, actually it's not cleaned up because cleaning up the statement, the stack frame, happens on line 14. So return actually simply jumps to line 14 in a sense. I find this very beautifully rendered by the debugger. Now, okay. Now stuff is happening. The call stack has been cleaned up. There is only one entry on the call stack, not two, because the one for largest has disappeared. But look, there's a special local variable, because the place where we store the return value is like this little place that exists between two stack frames, but stack frames are really a separation mechanism. So the return value is actually allocated among the locals of the main scope, or of the, in this case, of the calling scope, which is of course also the main scope for us today. And the return value is put in this special place, so the function is sort of given. And this is all happening implicitly, which I find beautiful. There's a lot of machinery needed to make this work in this intuitive way. So whatever is returned is actually put into this very special register of information. Beautiful. Anyway, so the function returned 3, and stack frame is cleaned up. Notice that the value has not been assigned to ABC yet. So this is just evaluating this expression. So the function is now a sort of expression. We take a step and now ABC gets evaluated to 3. And there we go. Wonderful, wonderful, wonderful. Every function defines a scope, and the scope will be activated by allocating space on top of the stack in a new stack frame whenever the function is called. And just like the variables declared inside the loop are not available outside the loop itself, otherwise we risk getting compiler errors and the subsequent outright refusal of the program to even run, the variables and parameters of a function cannot be used beyond the closing curly bracket that delimits the end of the body. And why is this important? This is important because functions are like this little universe that gets an input, the parameters, an output, whatever the function returns, and they perform a computation. And we want to isolate this little universe, this little isolated, separated program from the rest of the program so that there is no accidental mixing of variables. So suppose we have a rather trivial function, add x, y, and z, let's call this add3, that very simply returns x plus y plus z. Okay. And then we want to do something with x. And of course we get a compiler error because x is not defined in this context. It is defined inside the context obviously of add3, so here the compiler error disappears obviously. But outside the function, x doesn't exist. And why is this important? Yeah, because which x are we talking about? Every single call of the add3 function will generate a new x, a new y, and a new z. And, well, the call, the reading of x on line 14, which x does it refer to? And that's why we have this separation mechanism, which is truly important. On the other hand, a function can access all the variables defined in one of the parent scopes. For example, let's say that we have a variable size, which is the size of whatever figure we want to read. You know, I like doing this figure that we want to draw. You know, I like drawing little 2D figures on the console. I find it very cute. Okay, and then we want to build a checkerboard. And every single function that we will define for drawing will use the size. So the size is sort of a constant. Well, the variables defined inside the checkerboard function in its scope are private, cannot only exist within an invocation of this function. But variables defined before checkerboard, those are available. So size here can be used. Well, let's start by showing that we could, in principle, just print out the size. Oh, yes, of course, return empty string. There you go. But let's actually, well, let's actually do this. Let's actually build the checkerboard. Okay, so we start with clearly an empty result. Then we build all the rows. Wait, yes. Then for each row we go through all the columns. And, well, we add to the figure Let's do this with string interpolation, which allows the compiler to figure stuff out that we might be forgotten. If if the row is even and the column is even, or the row is odd and the column is odd, so row modulus 2 and column modulus 2 is the oddness or evenness of the row and the column, and we check that those are the same. So if they are the same, we add an asterisk, otherwise we leave this one empty. And after a whole row, so all the columns, then it's time to add a /n character. And at the end, we return the figure. Okay. So this is actually safe to do because the function checkerboard has been defined in a context where the size exists. So whenever I call checkerboard, so console.writeLine checkerboard, well, the size variable also still exists, but we will actually play a little bit with this later. Let me restart the building. And let's actually take a look at what the debugger, how the debugger shows this. I always like asking the debugger to just show how to represent this. Oh yeah, it's waiting for the for input. 7. This doesn't work at all. The read line. Okay, no problem. Let's make the program a little bit dumber. Let's go with a constant. Okay, we are here. Now we have the local scope that contains which also happens to be the global scope in this case. So the local scope of the main function or the main program is also called the global scope in some cases. Then we step into here. Okay, here what we have is figure and size. This is quite interesting. So the size belongs to both the local and the global scope. Okay, let's do something a little bit crazy. This makes little sense, honestly, because, well, checkerboard shouldn't change. It's not like every time you draw a checkerboard, then the size becomes bigger. I mean, okay, I've seen crazy requirements from when building software for the industry, but okay, this would sort of win the prize. Okay, so we have size is size plus 1 here. So you can see obviously size becomes 8 in this scope. And let's see in the global scope. In the global scope, size has also become 8. That's interesting because inside the checkerboard, it is visualized as... This is also why you can't entirely rely on the debugger. This is interesting. This is an important lesson actually to be learned. You can't fully rely on the debugger to understand exactly what is happening. So some knowledge of how the language works is fundamental. Otherwise, the debugger will look like it's crazy. So here, if you just inspect it as it looks like we have 2 size variables, and one of those is inside the scope of the checkerboard function. But that's not true, and there is no marking that shows that this would not be the case. That size is not just a variable inside the scope of checkerboard. It's sort of a warp gate from the scope of the checkerboard to the enclosing scope where size is declared, resulting in the fact that if we change size, it changes both inside the scope of checkerboard and in the global scope. The size variable, when a variable defined in a parent scope is included in the inner scope of a function, this actually has a name, and this is called the closure. We will talk about closures at the end of this lesson. All right. But before we do that, let's talk about something else. Functions may call each other. This is very useful and should not really be understated, because a function calling another function means that we can isolate the logic that each of these functions represents. And then, by having functions call each other, we can sort of build these chains of isolated computations where we can swap, modify, or play with the links, the individual links of this chain of modularized computations. So instead of having a program that is just a big block of code, we have a program that is made out of multiple functions that refer to each other, and every function is neatly and cleanly modularized. So the overload of thinking about the whole program is reduced into pieces, so we can reason about just one of these functions at a time, and if there is a bug, or we want to make a modification, or we want to predict what the program is going to do, or whatever, then we just need to think about the individual links and not the whole program, because if the program is big, it's going to be overwhelming to think about it, and eventually you run out of the single most precious resource in programming, which is your cognitive ability to reason about complex software, especially when dealing with concurrency and distributed systems, etc. And do make no mistake, it doesn't matter even if you're a genius. Eventually, the program will be bigger than what fits in your ability to reason easily. That's normal, and because no one, not even the biggest genius on earth, can think about, I don't know, the source code of even a modern, big-ish web application that does some interesting transactions. No one can. So we have to deal with this. We have to deal with isolation as a way for us to cope with the complexity of our software. Isolation, functions, and organization of code is all meant for the human, not for the machine. The machine seriously doesn't care. So let's say that we have 3 little functions. Now the example becomes a little bit more contrived. So we have a function f, take as input a string s, and returning the string s followed by an exclamation mark. When functions are so short and only feature a single return statement, we may omit the curly brackets and just define the function as follows. So arrow, the return expression, and that's it. Now let's call f with an empty string. Then let's define function g that has a question mark to the result of calling f of s. Mind you, and I'm also using s as the same parameter for a reason. And then h adds an at symbol to the result of calling g. Okay, so this is just a chain of functions calling each other. So h calls g, which calls f. So let's perhaps start by calling h, which is more useful. Let's run the debugger. There we go. Okay, so we step into, and we are at h. Okay, so you can see here we have the main program, and here we have, underscore h 02 line 12. Okay, whatever. We are at line h. We are at the function h. You can see it here where I put the mouse. Okay. Now, we cannot return the result yet, because in order to compute all of this, we need to know what g of s actually does. You can see in the local variables, there is s. Let's step into, okay, now here, g has been pushed on top of the stack. So here you can see the stack frame of g, which is underscore g, pipe 0 underscore 1. I have no idea why these names have been generated like this. Because these are probably treated like lambdas on variables. But anyway, it doesn't matter. Now, obviously, the result of this expression cannot be calculated yet, because we need to know what f returns. But for a second, okay, so right now we have the cursor stopped on line 14. So this is an active line. It's active, but at the same time, also it's frozen in waiting. It's waiting upon what? Well, it's waiting upon the return statement on line 12, which is not complete, which is waiting upon whatever G returns. Okay, so let's see what G returns. Oh, we cannot really determine what G returns because G is also waiting for the result of F. Okay, now you can see all the stack frames. Main, H, G, and F. F is the only one that's active. There is only for every thread in the program. So for now, for every program that we're going to write until we introduce multi-threading, there is only one line of code that is actually active, which is the one on line, which is the one on which is line 10 in our case. Okay, now we can return S, empty string, followed by exclamation mark. And notice that there are 3 instances of S. These are 3 separate variables, all called S. Because we have different scopes, within each scope we can find variables with the same names. There's no limitation that makes this impossible. So every scope may have the same variables. You can have the same variable S in a million scopes with the same or different types. Doesn't matter. This variable S will result in, this expression will result in, okay, look, this is beautiful, there's plenty. Okay, now, the concatenation of strings, but also especially F, you can see here, the scope, the stack frame of F has been popped, because now we only have main, H, and G, but not F anymore. But here inside the scope of G, we have the this little warp tunnel that before destroying the scope of S got the result out of it. That's okay, what came out of this call here, F of S, is just an exclamation mark, because we need this result in order, we have to store it somewhere. So there's a hidden variable, and here the debugger is very cleverly showing us this hidden variable where the return value has actually been stored, because it has to be put somewhere while G performs its computation. This is actually very pretty. Okay, then next step, okay, we pop the stack frame of G, so there's only H now, and look, G returned, and what's here? As you can imagine, exclamation mark and question mark. Okay, so the result of G of S has been stored now, and so it's beautiful because all of these return functions calling each other and returning directly is saving us from defining new variables, which might be very ugly temporary variables with very ugly names that are very, very complicated to understand. So yeah, this is a big deal actually, because it saves us our programs from the curse of being riddled with stupid variables, and the variables are just implicitly managed by the compiler and the runtime, like you see here in the scope. Anyway, then we go back and we can see that H returned, exclamation mark, question mark, and at, which gets printed out. Now, functions may call other functions, but they may also call themselves. A function that calls itself changes the arguments in order to re-instantiate itself on a new instance of the same problem. I love to make an example of recursive functions, which is, imagine that you have to eat something big, right? You have to eat a watermelon. Now, the strategy of, putting the watermelon in your mouth and swallowing is probably not going to work, because watermelons are on average bigger than human mouths. So the problem of eating the watermelon can be decomposed into 2 problems. Eating a bite out of the watermelon, let's say it's already open, you eat a bite or a spoonful, and then, well, you still have the problem of eating a watermelon, but with a bite less. And then you continue. So the problem of eating a watermelon where a bite has been taken, or 2 bites have been taken, or 3 bites have been taken, or 0 bites have been taken, it's always the same problem. It's always the same scenario that you have to tackle, But by eating just a bite, you haven't solved the whole problem. You have taken one step in reducing the problem. So the problem is the same, but it becomes smaller. Now, so let's say that we want to reverse a string. We want to reverse a string. So string ABC has to become CBA. So let's say that I want to reverse ABC. Well, reversing ABC, well, we could say, okay, let's remove character A. So reversing ABC is kind of okay. Take the first character, we put it at the end because that's what happens when you reverse, and then we still have to reverse BC. So you see, this is the byte we've taken out of the watermelon, and this is the rest of the watermelon. And yes, even though we're calling reverse again, which looks very weird because we're not really used to thinking about nested structures, and this is one of the reasons this nesting can lead to new dimensions. So programming is not a two-dimensional thing. It's nested. It is fractal. You can nest programs inside programs as a fractal. So one of these sort of structures where you keep zooming in, and there is the same amount of complexity even after you zoom in than there was at the top. Okay, but anyway, so, but of course, somewhere this thing has to stop. So when do you stop the watermelon thingy? Well, when the watermelon is completely eaten. So how do you reverse an empty string? This is the so-called base case. Well, if the string is empty, then that's it. You know already that reversing the empty string, you don't need to decompose anything. It's decomposed. You know the result already. So if someone gives you just the outside, the green outside of the watermelon, says, "Hey, eat this," you just say, "Okay, I'm done." You would probably also complain about, well, this makes no sense, but still. Well, you would be done immediately. There would be nothing to do. Okay, so if s.length is smaller or equal than 1, well, okay, we just return s. Oh, because, also reverse of the empty string, but also reverse of just one character, whatever that may be. Well, there's nothing to reverse because it's just one character. It's already specular. Okay, we could also say if it's smaller or equal than 0, or if, but then in this case we're skipping the one character, but we can also include the one character. That's nice. So the base case is also slightly smaller. So in this case it would be if the watermelon has no pulp left to eat, or just one spoonful. Well, you know what to do, right? You either just give it back or you eat that spoonful, and then, yeah, that's it. You know you're done already. Okay, you don't need to say, okay, I eat the last spoonful and then I check again carefully, is this a watermelon I need to eat? Oh no, it's empty. So you can sort of skip the last step or make it more streamlined. Okay. Then I'm going to use a cute trick. I'm going to take s minus the first character. Now, because s happens to be an array, a sequence of characters, there is a very pretty syntax that is the slicing operator. That means, okay, take all the characters of s, skipping the first one because the first one is at position 0. So s first character would be s of 0. I am anticipating arrays here. We will see them extensively later, but for now, just know that with the square brackets, I can just pick one of the characters, and with the square brackets with a range, so value dot dot value, I'm stating, okay, get the values between 1 and the last one, excluded. Okay, so now I can say, okay, now return. Let's take this expression, because this is a sort of our reference idea. This would be BC was the idea, okay, s minus the first character, and this would be s's first character. Let's run this. First, I want to see if we actually get what we're expecting. Yes, we get CBA, very good, always nice when things work in one go. Now let's look at the debugger. Let's jump in. Okay, first instance of reverse. The string s is ABC. Let's make the debugger window bigger. Okay, so we have the first character. Oh, sorry, we don't have the first character yet because we have to calculate. Okay, so first character is A. and s minus the first character is bc, and we did not early exit. We couldn't go into the base case because the length of s is 3. Oh, you can also see it here actually. String.length.get returned 3. Very nice this, because this way you can also see what the result was of the previous computations. This is brilliant. This debugger is is the best. I think the reason so many people use the C# and also Visual Studio is just this debugger has always been so complete and so much ahead of its time. But anyway, so because we can't enter the base case on line 11, we have to enter the recursive or inductive case. S minus the first character is only BC, whereas the first character is just A. Okay, very good. So we step into, okay, now what happens? We have the main scope, we have reverse called once with SABC, and we have reverse called the second time, the active one, with SBC. And BC is smaller than ABC, so we're closer to the solution, even though we haven't built the solution yet. And because it's smaller, it's the watermelon, but it's less of the watermelon left to eat. Okay, now we check. Length is 2, first character is B, the rest of the string is C, and now we reverse C. So now look, on top of the stack we have one frame ABC, one frame BC, one frame only C. Now you can feel it coming, the length is 1, so we can immediately return S, because string C is already reversed, or there is nothing to do to reverse it. So we go to the last, to the closing curly bracket. Let's take another step. Now you see one of the stack frames has disappeared. We go back to BC because BC here, it was waiting for this instance of reverse, the one of C, to finish. And look at this, reverse returned C, because whenever we destroy a stack frame, we also get, as the swan song of that stack frame that isn't among us anymore, we get whatever it returned. So here we go. And now we can calculate that, well, we got C plus the first character B. So this was BC and we had to turn it around. And now BC, turn it around, returned CB. Okay, so the string is ABC, BC turned around is CB, and to this we add the first character, which is A. And the function may now return CBA, and all instances of reverse are purged from the stack, and the program may terminate with CBA. These two variables are used only once. Especially this array slicing is a bit heavy, so it should go in a variable. But if it's used only once, we can just invoke it directly, and we get a slightly more elegant formulation. Also, well, we can refactor this into a conditional expression. When a function is only one single return statement, we can turn it into a lambda. And this means arrow, no curly brackets, no return statement, and especially eternal glory among all the people around you who will see that you are a top lead hacker. I am absolutely just kidding, but I find it quite elegant. All right. Now, I would advise you to go get a coffee now, because things are about to become a little challenging, because we're going to talk about higher order functions. Higher order functions are functions that manipulate other functions as a return parameter, as return values, or as input. Okay, so let's say that we have two functions, add3 These examples are contrived. And why do I mention this? Well, most of the examples we touch upon are, relatively speaking, contrived in this course. And this makes sense, right? Because, well, there will be courses later on, advanced courses, where we actually build some proper applications. But for now, we're just exploring the basics of the tools we are going to use for this. So the examples are smaller. These are not real-world examples. The topic we're going to dive into now, higher order functions, are only useful when building complex software. These are advanced modularization tools. I want you to see them because they are used already in frameworks and libraries that we will use. But these examples, they gain almost nothing from higher order functions. So it's just, building something meaningless with new materials. I ask for your forgiveness for this, but please be patient. Okay, so let's say we have these two similar functions. Add mul 3, and also, let's say, okay, this is enough. But you can imagine, okay, you could have multiple such functions that all basically look the same. Okay, whenever we see code that looks similar, and hopefully this is something you will learn to do immediately, because this is very important. It's super important to learn how to generalize this code so that you have only one instance of this almost duplicated code. So if code is duplicated, you just create a function for it and that's it. But what if code is almost duplicated? Like in this case, when we have three variables, they are the same, they have the same type, we return the same type, but the way we combine our three variables, that is the only thing that's different. So the difference is there, is significant. The proper way to generalize this is by saying, okay, you know what? The operation that combines two values, in our case by adding them together, this we will get as a parameter. So I will take both functions, I will put the functions next to each other. Okay, so this is, okay, the names, we have to figure out a new name that sort of encapsulates both of them. So add 3 mul 3, the parameters are the same, so I'm just putting them next to each other and then squishing the two definitions. And in our case, okay, the name has to be generalized, so we call it combine 3. And now, how do we squish this definition? Now, we can't, so it's sort of, okay, here we do something, and then we do the same thing again. Obviously, this doesn't work because the question mark is not an operator. Okay, so now we need to say, okay, do something with x and y, and then do something with the result of do something on x and y and z. Okay, this still doesn't work, obviously, because do something doesn't mean anything, but, well, that's a generalization. Now, this becomes interesting because I can say that do something, well, takes as input two integers and returns an integer, and so it's just a function. And now add 3 returns do something. Oh, combine 3, apologies. And what is do something in the case of add 3? Well, do something in this case will take two arguments, a and b, add them, and then do this on top of x, y, z. Let's first do this in a slightly different way. So let's say we have add of a and b returns a plus b, and combine 3 takes add as input. Yes, this is cleaner. And combine 3 here will take mul as input. And we're not really gaining a lot here. Now the program is bloating a bit, so that's why I anticipated we don't need these stupid functions to have a name. So if I have a function like this that just adds two integers, and I only use it here as a parameter to combine 3, because this here is the fragment, do something, that we instantiate in a whole of this computation, because this is a sort of computation with a whole, and the whole is how do you combine x and y, or the result of x and y together and z, you know. I like making a terrible example, so combine 3 is like cheese with holes, Gruyere. I think it's called Gruyere, I think I spelled it right. And then add 3 is like putting, let's say, nut paste in the holes, which some people actually do. It looks quite sophisticated in a restaurant. And mal 3 is like putting, in the holes of Gruyere. So it's still Gruyere, you know. And mal 3 is like putting, I don't know, tomato paste. And then you get this sort of sophisticated cheese presentation where inside the cheese you can put, let's say this is truffle paste, yes, so let's make it even more sophisticated. Now, obviously, so the main thing is the Gruyere, you know, and it has the same structure and the same holes, but you put something else, and then, well, the result is different, but it's still sort of Gruyere. That's sort of the template of what you're serving, while also being more than just Gruyere, you know? Okay. Now, this little function is kind of ugly, so it is possible to just say, okay, you know what, I don't want to define the function and pass it by name, but just put the body of the function, like this. So you literally take the body of the function as a lambda, and just put it there. But, and this is actually quite cool, you don't need the declarations of the parameters, and you know why? Because combine 3 already knows that do something takes as input 2 integers, and so it already knows it's completely redundant. A and B are supposed to be integers. Whereas if you define the function separately, like we did before with add, well, then that is disconnected from combine 3, so the compiler has no clue that A and B are supposed to be integers. This is called the type inference. The types of parameters is inferred, is guessed from the context. Okay. Now, well, why not? Given that we're only calling combine 3. Okay, cool. So, compose 3 or combine 3 has a hole, and you can actually use it however you want. Like you could say, okay, but what if I just want to have something that divides in sequence? Okay, no problem. What if I want to have something that, I don't know, elevates to power in sequence? Well, also, why would this be a problem? Oh, apologies. Math dot pow of A and B, which we have to cast to an integer because it returns a double. Okay, very good, and so on. Like we can really do whatever we want with this little combine 3 function. So it's already okay. It's still trivial because you're probably not going to write this, but the principle of you notice that your code is similar but not quite, and still you want to generalize it, because let's say that you want to add some printing, some logging, a console.write line because there's an issue somewhere and you want to see whenever combine 3 is called, or you want to save it, or you want to memorize all these calls for safekeeping of what your program ended up doing or whatever. Now you can do it in just one place, and then changing combine 3 changes all the instances of add 3, mul 3, div 3, pow 3, and a potential infinity of other places where we're using the same logic of squeezing together 3 values according to a 2x2 squeezing principle. This is beautiful, actually. This is beautiful and elegant. Oh, by now I think we can remove this bit. I think it's clear, the template of functions. But combine 3 actually, and now it becomes quite surprising, combine 3 may take its parameters in a different order. So combine 3 actually, it's the real parameter of combine 3 is how to combine the values. It's how to complete the algorithm. These parameters x, y, and z are properly only the parameters of add 3, mul 3, div 3, and pow 3. And you can see actually that here, inside add 3, this parameter, the do something function, is already known. This is it. This is the parameter. Whereas x, y, and z, we're still waiting. You know, x, y, and z, we wait for them. But here, when defining add 3, combine 3 is known, is the first parameter of combine 3 is known. The other 3 we still have to wait for the call, which happens on line 18. So you can see that combine 3 gets its parameters in a given order, and this order is very important. So do something is the only parameter of combine 3. And then combine 3 returns a function that expects the next round of parameters. And I'm going to use the lambda syntax now. Okay, so what does this mean? This means that, okay, now combine 3 takes as input the function do something and returns a function that takes as input x, y, and z and returns the final integer. We could have also said, okay, do it like this. It's also possible, but it's a bit uglier. And also, well, this function we can use the full syntax. I don't like it at this point. Oh no, this has to be a lambda. We can put the curly brackets, but they are quite pointless. Oh, there we go, because it's an expression. I find this overly complicated, to be honest. So I will remove the curly brackets. There you go, curly brackets, go. Yes, and here we are. Now look at what's happened at combine 3 here. Because combine 3 now takes only one parameter. You can also see it in the IntelliSense. It only shows that it wants just one parameter. It doesn't want all of them at the same time. So I call combine 3 with a plus ab goes into a plus b, so just the sum function. And what does this give me back? Well, calling combine 3 with the do something parameter gives me back the underlying function where, okay, we now get the parameters and we actually apply do something to them. So now this is the function that takes as input x, y, and z. The same applies to these other functions. So first we pass one parameter, that's the do something function, and then we pass x, y, z. I hope you are ready to get your mind absolutely blown to outer space. So if you're standing on the edge of a dangerous trail, you might want to stop watching the video because you might fall down in just sheer excitement and transcendence. All right? So you've been warned. Please sit down, take a breath, and look at this beauty. Add 3, we can define it as just a variable because this repetition of the parameters is actually quite unnecessary. We can say that add 3 is a function created by simply giving the first parameter to combine 3. So add 3 is the combination of 3 parameters according to a do something function, which just adds them together. And you might be wondering, oh my god, where are the x, y, and z? Well, the x, y, and z, they are defined here already. Combine 3 is still waiting for those 3 parameters, and because combine 3, after giving just do something, waits for the 3 parameters, so does add 3. And if you look at the type of add 3, it's a function that takes as input 1, 2, 3 parameters and returns an integer. The same applies to mul3. And notice also that I am just allowing mul3 and add3 to be declared as, well, actually as constants, because I don't want to redefine them. Const var const. Doesn't matter, you know. Let's just define them as variables for now. I don't want to distract myself. Okay, so div3 is combined where do something is the division, and pow3 is combined with exponentiation. What's actually amazing about this is that now we are not only reusing the logic of combine 3 for 4 relatively different functions, which are add3, mul3, div3, and pow3, but also we don't have those ugly parameters x, y, and z because they are defined implicitly. And so we have defined combine 3 as a staged computation, or now combine 3 is a curried function, meaning that it receives its parameters in different batches. after one batch is given, we still have a function that expects parameters starting from the first unspecified batch. So the batches are, in this case, do something. So do something is the first batch, and x, y, and z is the second batch. So when we specify do something, now we have still a function that expects the next batch being x, y, and z. Very beautiful, very elegant. And by specifying, because usually when you have a computation that you generalize, the functions we pass as parameters belong to the first batch. The first batch specifies how to instantiate the computation, so the holes in the Groovier, and then the next batches are just the concrete actual values that we want to pass to actually perform the computation concretely. So first you specify the holes in the computation, then you specify the actual parameters for the previously specified computation. We have seen so much in this class that I hope you're not overwhelmed. These are videos, you may watch them as much as you want. My advice now is be patient. Learning a programming language, like learning a real language, a foreign language, takes massive effort, massive repetition. It changes and restructures your brain. It changes the way your brain processes and structures information. Love this process, enjoy it. Don't be overwhelmed by frustration. Allow this thing to change the way you look at reality. The payoff is, and you may skip this bit if you're bored, because this is not about programming, it's about, life in general, if you will. Whenever you learn a language and a new way of organizing thought, your perspective on reality enriches. So you gain new tools to think about the world, in abstract and concrete terms. This makes you a different human being, and to an extent, most likely a better one, because having more ways to look at the world gives you a richer, deeper perspective on life. But this process of shifting and readjusting the world and discovering a new you in the process also, because having a new perspective on the world gives you a new way to be yourself. This requires your mind to shift and adapt, and it is a slow process, and there is nothing around the slowness of this process. And this can be frustrating if all you want to do is learn and become fluent and get a job and get money. And I understand, obviously, especially if you're under any sort of pressure, this is terrible. It's terrible to feel that you have to perform and to feel that your stupid brain is not adjusting quick enough. Damn, why isn't it adjusting quick enough? It's life. Breathe. Ground. Fall in love with the beauty of these things, because these things are incredibly beautiful and sophisticated. Realize that you're discovering a new way of using your mind to explore reality, and this has infinite value. Nothing comparable in any way to the pathetic value of earning a little bit more money in your job. Learning to look at the world from new eyes, to have a broader mind and perspective on categorizing information is something that only deserves love, patience, and attention. Allow yourself this. I wish you absolutely the best of luck in your learning path. Stay strong, enjoy, and see you very, very soon.